Dear students, as a continuation of my lecture on acids and bases, this is my 5th lecture. So in my last class I finished with the Gutman's rule. Here I would conclude this topic with few more examples. Here you see that the silicon fluoride SiF4 compound and SiF62 minus complex ion is cited here. So you have to compare them according to their bond length, the silicon fluorine bond length. Now silicon tetrafluoride is an acid. It reacts with F minus ions, which is a base. So after forming an adduct with simultaneous combination with two F minus ions, this SiF62 minus complex ion is formed. Now what happens? In SiF4, silicon is partially positive due to high electronegativity of fluorine. Now when it forms the adduct with F minus ion, then this partial positivity character of silicon reduces. As a result, the polarity of this bond also reduces. This results in lengthening of the silicon fluorine bond length. So that is why we find that the bond length of SiF in SiF4 is less than that in SiF62 minus ion. This is 154 picometer and this is 171 picometer, which is substantially higher than the previous one. Similarly, SbCl5 antimony pentachloride, when reacts with chloride ion, which is an acid-base reaction, this is acid and Cl minus is a base, then the same thing happens. The partial positive character of the Sb or antimony atom decreases. As a result, the lengthening of the bond takes place. So the bond length of the SbCl increases from 231 picometer to 247 picometer. So if you are asked that compare the bond lengths of these compounds, then you will show that the acids, the previous acids before forming the adduct, have shorter bond length. And as an explanation from the Gutman's rule, you will explain that the partial positive character decreases. As a result, the polarity of the bond decreases and bond lengthening takes place. So similar two more examples. When sulfur dioxide reacts with O2 minus, this is also an acid base reaction. On the other hand, iodine reacts with I minus, this is another acid base reaction. In both cases, lengthening of bond takes place. Now we move on to a fresh topic, which is strengths of the oxoacids. So what are oxoacids? From your lower classes, you are dealing with lots of oxoacids such as sulfuric acid, nitric acid, carbonic acid, phosphoric acid, etc. So we have to compare different types of oxoacids according to the strengths of their acidity and basicity. Actually, according to their acidity. So when an element X forms acids of the type HXON, for example, perchloric acid HClO4 or HNO3, H2XON, for example, sulfuric acid H2SO4, carbonic acid H2CO3, HMXNOP, for example, oleum H2S2O7 or thiosulfuric acid H2S2O3. So etc. types of compounds having XOH type of bonding. This is the site where acidity develops due to high electronegativity of oxygen. When there is some OH bond attached with some electronegative element, then this site is highly acidic. This bond breaks and the proton is released. So this type of bonding is present. So these substances are known as oxoacids or oxyacids. Okay, you have a series of oxyacids of chlorine, bromine, sulfur, selenium, nitrogen, phosphorus, etc. So how would you compare them? The greater the electronegativity of the central atom X, this X is the central atom, okay, so it must be electronegative, such as phosphorus, chlorine, nitrogen, all these are sulfur, all these are electronegative, substantially electronegative element. So when these are attached with OH minus, OH moiety, then acidity develops. So according to their electronegativity, the acidic character also changes. So higher the electronegativity, more will be the acidity, because the more it will pull electrons from oxygen onto itself. So electron being pulled from here to oxygen, then from oxygen to here. So this side becomes very much vulnerable and it is ready to break, and the electrons must be shifted towards the left hand side, and hydrogen would be released as the proton. The oxygen in its turn will pull electrons from hydrogen. Okay, oxygen is pulling the electron as the part of inductive effect. Thus dissociation of an oxyacid is dictated more by the electronegativity of the central atom by the other factors. So the OH part is common. So this part, when becomes uncommon, then the electronegativity would decide which one would be more acidic. So more the electronegative, more will be the acidic. But there must be some exceptions also. Actually not exceptions, there are good explanations behind all the things happening regarding acidity. So we shall discuss more elaborately with few more examples here. Now you know that acidity, when Ka decreases, pK increases. Okay, so it is more dissociating, so more higher value of Ka, and it is more acidic. So acidity, according to the group of periodic table, acidity decreases. Okay, now what is the explanation? Such as in the elements form the oxyacids, such as hypochlorous acid, hyperbromous acid, and hypoiodous acid. So which one is the most acidic substance? Definitely we have to consider according to the electronegativity of the central atom. Here chlorine is the central atom, here bromine is the central atom, and here iodine is the central atom, and OH moiety is common in all these three. So chlorine has the highest electronegativity, so HOCl should be highest acidic. Similarly, in HClO2, that means chlorous acid, this is hypochlorous, this is chlorous acid, then hyperbromous acid, then iodous acid. So chlorous acid definitely, as chlorine being most electronegative, chlorous acid would be the most acidic one, and iodous acid would be the least one. Similarly, chloric acid is highest acidic, then bromic acid, then iodic acid. Okay, and finally perchloric acid, perbromic acid, and periodic acid. Among them, perchloric acid is the most acidic substance. In fact, perchloric acid is the highest acidic substance in the universe. There are few more examples of superacids, but if a simple single acid is considered, then perchloric acid is the highest acidic substance in the universe. Okay, now move on to the chalcogen group, where sulfur, selenium, and tellurium forms the H2XON type of acids. Then highest electronegativity has sulfur, and lowest electronegativity has tellurium. So sulfurous acid is more acidic than selenious acid, which is further more acidic than tellurious acid. So H2SO3, sulfurous acid, H2ACO3, selenious acid, H2TeO3, tellurious acid. Among them, H2SO3 has the highest acidity, and H2TeO3, tellurious acid, has the lowest acidity. Now, if in the previous examples, if the central atom is common, but the oxidation number is changing, such as HOCl, then HClO2, then HClO3, and then HClO4. Here the oxidation number of chlorine is +1, where it is +3, here it is +5, and here it is +7. So which should be the highest acidity? Definitely perchloric acid would be having the highest acidity among this. So this example is compared here. HClO4 more acidic than HClO3, more acidic than HClO2, and it is further more acidic than HClO. Similarly, sulfuric acid and sulfurous acid. Sulfuric acid must be more acidic, having the highest oxidation number, because this is sulfur having oxidation number +6, while this one having oxidation number +4. Similarly, here also nitrogen having oxidation number +5, and here in HNO2 nitrogen having oxidation number +3. So nitric acid is more acidic than nitrous acid. Now here is some exception. Similarly, from the previous example, we can say that phosphoric acid H3PO4 should have highest acidity among all these type of acids, such as phosphorus acid and hypophosphorus acid. But here it seems to be an exception. There is a good explanation behind this. Look at this picture. Actually, this phosphoric acid H3PO4 is tribasic. It has 3 OH sites, whereas phosphorus acid has 2 OH sites. On the other hand, conversely, monobasic acid is this one. So having 3 OH, having 2 OH, and having 1 OH site. But each phosphorus is attached with 1 oxygen. Here 1 oxygen, here 1 oxygen, here 1 oxygen. This oxygen is pulling the electrons from phosphorus, having higher electronegativity due to its inductive effect, -I effect. And acidity develops due to the fragmentation of the OH bond. But here you find that there are some H bond P type of bonds also, which are not at all responsible for their acidity. That is why this hydrogen is not will not increase the basicity of this acid. That means this hydrogen is not having a protonic character, because there is very little difference in between the electronegativity of phosphorus and hydrogen. They are almost same, in the range of 2.1 to 2.2. But there is difference in electronegativity of oxygen and hydrogen. So electron must be pulled by this oxygen, and this will be distributed. This will be further pulled by this oxygen. Now the pulling effect of electron of this double bond O will be distributed over 3 OH moieties here. On the other hand, the pulling effect of electron from the double bond O will be distributed over these 2 moieties. And finally, the pulling effect of electron due to inductive effect of this oxygen will be distributed over only 1 moiety. So which one would feel the highest pulling of electron? Definitely this one would feel the highest pulling of electron. It will accelerate the fragmentation of this bond, and definitely this would be the this will have the highest protonic character. So what is explained here? The hydrogen atom bonded directly to phosphorus are not acidic, as its P bond H bond is not polar enough due to equal electronegativity of phosphorus and nitrogen. That means H bond P, this is not at all acidic due to very lower difference in electronegativity, almost similar. Acidity arises from the O bond H groups, the number of which in H3PO2 is 1, in phosphorus acid is 2, and in phosphoric acid are 3, for which these oxyacids are monobasic, dibasic and tribasic respectively. The inductive effect of the doubly bonded oxygen atom acts on the single O bond H bond in H3PO2, but it is distributed over 2 and 3 OH bonds in here and here respectively. So due to the distribution of the pooling effect of this electron from this oxygen, they will feel least pooling, so they will be least acidic. So this question is very important. Among phosphoric acid, phosphorus acid and hypophosphorus acid, which one has the highest acidity, or arrange them according to their increasing acidity or basicity. So this will be highest acidic according to the decreasing acidity. After phosphorus acid, hypophosphorus acid, phosphorus acid would come, then it will be followed by phosphoric acid. So these are the strengths of oxyacids and the exceptions also. So that's all for today. Thank you.